So this is a problem that took me 17 minutes and I was trying to go fast, so we'll see how this goes. So we're given RC is 0.6 feet, so let me just draw that in a picture. That's 0.6 feet. We're also given that theta dot equals 0.4 radians per second, and theta double dot 0.9 radians per second squared. We're going to need to get R dot and R double dot. It's going to involve some calculus, so let's just go ahead and start with that before I do the free body diagram. So R equals 2RC cos theta. R dot is 2RC minus sine theta, theta dot, okay, minus 2RC sine theta, theta dot. And so then R double dot using the product and chain rule will be minus 2RC cos theta, theta dot, theta dot, plus sine theta, theta double dot. It took me some time to plug in the numbers. We'll do that a little later. Okay, so now let's draw the free body diagram and continue from there. So here's the pin. If this is 25 degrees, this angle will be 50 degrees. That's a geometry fact, and where it comes from. If that's 25 because there are two radii, this has to be 25 degrees. And so 25 plus 25 is 50. 50 minus 180 is 130 here. And then 130 plus 50 again equals 180, so that's why that's 50. So what we know is that the force of the circle, which is normal to that, I'm going to call it force of the circle, has to be at 50 degrees. And then I'm going to dot in the arm, which is at 25 degrees. And so normal to that is the force of the rod. And that is at this 25 degrees from vertical. And this is also a vertical circular path, so there's gravity. So that's mg. Okay, and so what that will equal to is, I'm going to dot in the r, the radius again at 25 degrees. M times the radial acceleration, which is on your sheet, but I've just got it memorized. You've done it so many times. R double dot minus the centripetal acceleration, which is r dot v squared over r, which is also r theta dot squared. And the transverse theta acceleration is r times the angular acceleration plus the weird 2r dot theta dot thing. Okay, so there we go. So to solve this, we're gonna have to plug in r dot, theta dot. And the reason it took me so long when I was going full blast is I went too fast and I multiplied the acceleration by m, and I realized, oh no, it only wanted the acceleration first, then m times, so I had to recalculate things twice. So it actually might go faster here. Okay, so we were given theta dot is 0.4 and theta double dot is 0.9. So I'm going to calculate r. So r is 2 times rc, which is 0.6, times the cosine theta. I'm going to just write c for cosine, and I'm going to just store the sine and cosine and calculate it out later. R dot is minus 2 times rc, 0.6, times sine times theta dot, which is 0.4, and r double dot, scoot out here, is minus 2 times RC, which is 0.6, times cosine times theta dot squared, which is 0.4 squared, plus sine times theta double dot, which is 0.9. Okay, so I'm actually going to calculate cosine and sine, store those in my calculator, and then run these out. I'll be right back. So I get R is 1.0876 feet. And what I do is my calculator can store numbers, so I'm storing that in register 4 so I don't have to type it again later. And R dot is minus 0.2029 feet per second, and I'm storing that in register 5 on my calculator. And R double dot comes out to be 0.6304 feet per second squared, and I'm storing that in register 6. And so when I was flying through the test, I multiplied the next step I'm about to do by the mass, and I had to undo it. So if you read carefully, it's saying what's the acceleration in r and theta, so we have to do that first. So I'm going to do that correctly now. So I'm going to do AR, okay? So that is just r double dot minus r theta dot squared, and a theta is r theta double dot plus 2r dot theta dot. Okay, so I'm going to do that, and then I've got r dot and r double dot already stored in my calculator, so it'll make things go a little faster for me. So it's kind of funny, now that I'm going slow, I'm making more mistakes than when I went fast. I forgot the negative sign on r double dot earlier, but I did catch it before I continued. So r double dot was minus 0.6304. So r double dot minus r theta dot squared ends up being minus 0.8044 meters per second squared. Negative means it's going in. And plugging in the values for r dot, etc., I get 0.8165 meters per second squared positive, meaning going that way. So I'm going to write those in. Okay, so now we need to get the forces, and I'm going to go back up to the free body diagram. Okay, since I'm doing this slowly now and I have all the time I need, I redrew the free body diagram. I multiplied the accelerations by the mass, and the mass is half a pound divided by 32.2. And during the test, it just struck me that these forces were really tiny, 0.0125 pounds and 0.0126 pounds. I was a little worried that I got it right, but I felt like I didn't have time to press on. To go over it, so I just kept pressing on. Okay, and so I made the decision when I was taking the test to use the r and theta directions, which I think was the right choice. And so I'm going to stick with that here. You might try x and y, but I think it's kind of like a problem. So I'm going to use that direction and that direction. Okay, and so what that does, so it was, I had to figure out, okay, this little angle between the circle and the rod, and this slowed me down quite a bit. It was hard for me to figure this out. And so what I eventually did was I looked at this triangle. So that made this 40 degrees. Then I looked at this right angle. And so I did the math in my head. 40 plus 25 is 65 minus 90. That was 25 degrees. And so that just threw me for a loop, that it was 25 degrees again. And so I spent quite a bit of time thinking about it and double checking it in my head, and that slowed me down quite a bit. But that is correct. That is 25 degrees there. Okay, so once I had that all figured out in my mind, I noticed, yeah, we can easily solve for the force in the rod, the force in the circle using these coordinates. I also had to get this angle, and I convinced myself that that was 25 degrees because of this angle had to equal that angle. Okay, so we were all ready. I was all ready to continue, and so now when I looked at this, I noticed that if I sum forces in a theta direction, I would have F rod plus F circle sine 25. I wouldn't solve it. So just to save a little bit of time, I did sum forces in the R direction first, because it would just have the circle component. So let's do that. Sum forces in the R direction will equal MAR. Okay, and then once I convinced myself that angle was 25 degrees, I had F circle cos 25 degrees minus 0.5 sine 25 degrees. The rod force did not have any component in the R direction because it's perpendicular to the rod. And the acceleration, mass times acceleration in the R direction was minus, because it's going in, 0.0125 pounds. And then I just solve for F circle. And I got the force of the circle onto that pin was 0.219 pounds coming out. Okay, then once I knew that, I did some force in the theta is mass times A theta. And so doing that, you have the force in the rod, and then taking that way as positive. And then when we did the radius one, that was positive. So taking counterclockwise is positive as always. You get the force of the rod plus the force of the circle, which we already just solved for, sine 25 degrees, minus the weight, 0.5 pounds, times cosine 25 degrees, equals 0.0126 pounds. Okay, and then I then just solved for the force on the rod after I put in that the force of the circle was 0.219. And that came out to 0.373 pounds, positive mean that way. Okay, so writing in the answers, I had a hard time. I had to look at what P and OA were. So OA was the rod, and so this was the force of the rod on the circle, and then this was, the rod on the pin, and this was the circle on the pin. And so once I did that, I figured out that that was 3.73 pounds going that way, and the pin on the circle was 0.219 pounds going that way at 50 degrees, and so this was from the vertical 25 degrees. Okay, and I checked and I got that right, and let me go see if I got it right when I took the test. Okay, so I just looked at the test that I did, and I actually got one wrong. So I somehow got this wrong, which means I calculated that wrong. And I was flying when I was throwing in the numbers, and not exactly what I did wrong. I probably forgot that too. But amazingly, everything else was right. And what saved me was these forces are so small. So the error I made in A theta, it changed this number, but these were so small. It didn't change the answer except in the 1,000th place. So I actually got the forces right. But if I was grading it, I don't know, I probably would have taken, it's a 20-point problem, 5 for each of these steps. Yeah, that was maybe 1 or 2 points off for doing everything right but punching that out wrong. And because I got the number right for the force in the theta direction, I just let that slide, and I would let it slide for you. So yeah, it worked out great that the accelerations were so tiny, that these m times a's were so small, that even though I messed that up, I still got the problem right. I mean, these forces on the right-hand side are so small, it's almost like a statics problem, almost zero on that side. Okay, but certainly I wouldn't grade it like that. If you got a lot of points off if you didn't have the MA, because you wouldn't have AR and A theta, which is 10 points right there out of the 20. Okay, so let me go on to the next problem. So I just realized that